Okay, looking into the next portion, okay, we have regarding linear independence, and we have an index set of vectors, okay, where we have going from v of 1 to v of p, and Rn is said to be linearly independent if the vector equation, where we have x1 v1 plus x2 v2 all the way up to xp vp is equal to 0, has only the trivial solution, okay, where we have for the weights x1, x2, all the way up to x of p, will all be equal to 0. And now the system is consistent and there is no free variable. Okay, and now just a case of what we have regarding linear independence. Let's say if we have three vectors. Okay, so you have v of 1, we have 140, v of 2, we have 252, and v of 3, we have 361. And it says to determine if the set is linearly independent. Okay, and it's going to be linearly independent if we have only, okay, our weights x1, x2, and x3 to come out to 0. So applying what we have here, okay, so performing row operations on the associated augmented matrix. Okay, and just a little bit of a segue. Okay, so again, we have with our vector equation, we have x1 v of 1, x of 2 v of 2, x of 3 v of 3 is equal to 0. And we have translating this again to the matrix equation. Okay, so we have, again, for this portion, okay, this is going to be the vector equation. We have in this setup, okay, we have, once again, we have the matrix equation and performing row operations on the associated augmented matrix. Okay, so we have in the setup, okay, so you have in this one, okay, so in the augmented matrix form, okay, so we have going column by column, we have 140, 252, 361, and we have is equal to 0 in the matrix. Okay, just getting it to reduced echelon form. Okay, so I'm going to make the second row first element into a 0, so I can take second row minus 4 times the elements from the first row. So I have 0, negative 3, negative 6 is 0, and okay, and then we have next, okay, our second pivot position will be where the negative 3 is situated, and I want to make this into a positive 1, so I can take negative 1/3 of the second row. So I have this set up, and just continuing on as we progress to the reduced echelon form. So I'm going to take twice the second row from R of 1 and R of 3, and I have this set up, and then where we have the final pivot position where negative 3 is located, I'm going to make this into positive 1 if I take negative 1/3 of the third row. And so I have 0, 0, 1, 0, and then finally performing the necessary operations to get to the reduced echelon form. It's going to turn out that x of 1, x of 2, and x of 3 will all be 0. And so in this case, this particular system is going to be linearly independent, since there is the only trivial solution where we have x of 1 equal to x of 2 equal to 3 equal to 0. And so for what we have at the other end of the spectrum, now we have for the same index set, this will be said to be linearly dependent if there happen to exist weights not all 0, such that the vector equation is equal to 0. And the system is going to have not a trivial solution where we have all zeros, but instead a non-trivial solution where there is at least one free variable. Okay, so we're going back into the terrain of free variables. And as an example, okay, say we're looking at determining if the following set of vectors is going to be linearly independent or dependent, and if possible, should there be a linear dependence, find a relation among v of 1, v of 2, and v of 3. And we'll take, just as an example, we'll say that we have v of 1 equal to 102, v of 2 equal to 214, and we have v of 3 equal to 316. All right, so going through, again, just our little protocols. Again, we have with the vector equation, Okay, we have this set up, and again we have the matrix equation, okay, resulting from what we have for V of 1, V of 2, V of 3, and also with the weights x of 1, x of 2, and x of 3, and translating what we have as an augmented matrix and performing the necessary operations. Okay, so we have 1, 2, 3, 0, 0, 1, 1, 0, 2, 4, 6, 0, and getting the conversion of 2 to 0. I'm going to take twice the first row elements from the last row, so I'm going to have zeros to run across, and I have, and then following through, if I take twice the second row elements from the top row, we have 1, 0, 1, 0, 0, 1, 1, 0, and we have 0, 0, 0, 0, and in this particular case, right, this is as far as we can get. And just for translating out, okay, we're going to have the x of 1 plus x of 3 is equal to 0. So we're going to have additive inverses with x of 1 and x of 3. Likewise, we're going to have x of 2 plus x of 3 is equal to 0. So we have x of 2 equal to negative x of 3. And again, since there is no pivot position in the third column, we have the x of 3 is going to be a free variable. So we're going to have a non-trivial solution, whereupon we have x is equal to x of 1, x of 2, x of 3. And again, rewriting, we have x of 3, and we have times the vector negative 1, negative 1, 1. And so we have, for this set, okay, this will come out to be linearly dependent. Okay, so going back to the other portion, okay, so we have linear dependence. And it says, if possible, find a linear dependence relation among V of 1, V of 2, and V of 3. And again, we had our non-trivial solution, which resulted that x of 1 and x of 3 are additive inverses, as are x of 2 and x of 3. And we have where x of 3 is free. And just for a sample, okay, we can choose any non-zero value for x of 3, and we'll just say arbitrarily that x of 3 is equal to 10. And so if x of 3 is at 10, we're going to have additive inverses from x of 1 and x of 2, where each of these values will be at negative 10. And just going back to what we have for the generalized form of the vector equation, x1 v1, x2 v2 plus x3 v3 is equal to 0. We're going to have negative 10 v1 minus 10 v2 plus 10 v3 is equal to 0. Okay, so that's just a sample equation, okay, expressing linear dependence.